Okay, so let's talk about our last topic that's going to be included on that Unit 3 test coming up on Wednesday. And this is the idea of adding vectors. Now, I saved this for last because there really isn't anything new to this. And we've already kind of sort of done a little bit of this, and you'll see what I mean when we get into this. It's just a different way of thinking about the motion of objects, especially in two dimensions. When there's an X component and a Y component. Now think about what vectors are. You know what a vector is. A vector is something that has both a magnitude, which is just a fancy way of saying a number, which is typically called a scalar. A number by itself is just a scalar quantity. But what makes a scalar a vector, what makes a number become a vector is you also have a direction. So vectors have magnitude and direction, and these are physical quantities. We understand the physical concept of velocity and acceleration and displacement, moving from one place to another. Well, you can have more than one vector over the course of something's motion. And we've seen that with projectile problems. We know there's motion in the X going this way, and then there's a motion in the Y. And the combination of those two is what the motion of the object is. So let's talk about how we do the mathematical approach to taking two separate vectors and then combining them and getting what's called the resultant or the final vector. We're going to start off with displacement. Displacement is how far you have moved from some point and what direction you have moved. So if you imagine somebody starting off here, and it's convenient to think about starting off with the origin, and we'll describe a path. Let's say a person walks, we call this north, like our typical cardinal directions. This would be east, west, and of course, going down this way would then be south. So consider a person who starts off at the origin, which your starting point is always going to be your origin in these problems because you haven't started your trip yet. So your origin is wherever you're at. And let's say a person walks east 5 miles, 5 kilometers, 5 feet, doesn't really matter. We'll say he walks east 5 units, we'll call it miles. And then the person changes their motion. And we've seen how motion changes all the time. And then let's say this person decides to turn and go due north. And let's say if that's 5, we're going to call this maybe 8 miles. So now we've got two different vectors that describe this person's motion. It's both how far and in what direction. We had that segment. Well, then the person's motion changed, and we had another vector that described the motion. It was 8 miles and this way. Notice when I drew these arrows, I drew one arrow that was bigger than the other, because when we represent vectors with arrows, we try to make them in terms of scale somewhat correct. Now, I didn't take a ruler out and measure these, but I don't want to draw the one that represents an 8-mile trip smaller than the one that represents a 5-mile trip. We'll do some of these on graph paper, and that'll make it a little bit easier for us to get the scale right, because the scale gives us a physical indication of what this motion would look like. Okay, so here now we got this person, and they're right there. Now, if we want to describe their motion, well, we've got two different vectors that we can add together. The result of this person's motion, in the end, the person was here and the person wound up here. That is also a distance, a number, and it's also a direction. So in the end, the result of the person's motion was basically that he went from here to here. Now, he didn't walk that path to get there. He went this way and this way. But the result of his motion, the end result was he started here and he ended here. The resultant is the final vector. It's what you get when you add up any other vectors that's affecting something's motion. And in this case here, it's kind of easy to see that we made a little right triangle because the person went due east and then went due north. So a little right triangle here, where my resultant is the hypotenuse of my motion. Now, I can find out how far that is. How far did the person wind up from where they started? And that's a physics term called displacement. So we want to get the displacement, and the displacement is the result or the resultant vector of his two segments added together. Well, we see because this is a right triangle, we know that a squared plus b squared equals c squared, where c is that side of the triangle. So I could take 25, because that'd be 5 squared, plus 64 equals c squared. C would equal the square root of 89. And that's the length here. That's how far I wound up from where I started. And that's the result of my two separate paths combined. Now, this becomes the number part of my resultant. The directional part of the component would be measured by that angle there. And we know enough about trig and that SOHCAHTOA that if we're given the three sides of the triangle, we know we can figure out what angle this is. And we won't necessarily go through this math right now. And there isn't any specific math where we find the angle on this particular unit, but it's coming. It's next unit that becomes very important. For a displacement vector, we would say whatever the square root of 89 is, was that 9? It's going to be 9 point something. It's 9 point something miles. So the person wound up 9.1 miles from where they started at some direction northeast. And we could find that angle northeast by doing SOHCAHTOA. Okay. Now, it doesn't have to be just two vectors. It can actually be multiple vectors. And we're going to look at this graphically, and we're going to do some math. Let's say I don't start off going due east. Let's say I go that way, that angle. That's my first trip. And then my second trip, I wind up. Oh, I turn around and say, no, I made a mistake. I want to go over here. Now, in the end, what is the result? The result is I started here and I wound up there. So that would be my resultant. It's the sum of all of my vectors together. Now, we can also do the math on this, and let's look at this. Think about my x. For this first part of my x, I went that distant in the positive direction. Okay. But then I turned around and I went a lot longer way in the negative x direction. I went a lot more than that distance, and I went more into the negative side. So my final x, my resulting x, ends up being negative because I went up more this way from where I started, as opposed to the last problem that I wound up on the positive direction in x from where I started. So my resultant would be some value in x, some value in y. I can figure out what that is using the Pythagorean theorem, and I can get that angle. For now, we just have to understand the concept. I need you to understand the concept that you can have multiple vectors, and in the end, when we add them all up, we get some end result. And this can be any number of vectors. Start off going that way. Then maybe I turn around and go this direction. Then I go there. I can do this over and over again. If I walk that path, my net result, my resultant is that right there. Because that's how far I wound up from where I started, and that's what direction I wound up from where I started. So for now, we're going to do this graphically. We just need to realize, okay, in the end, that's what I call my resultant. That's the sum of all of these little trips added up. In the end, they combined to make me have a trip where it seemed like I went from there to there. Now, this doesn't have to be just displacement. Displacement's a vector, but we also know that velocity is a vector. So any vectors can be added together. So let's consider a baseball here. And let's say it is thrown through the air. And we know as soon as it gets thrown, it's going to drop like a free fall problem. Okay? That ball is going to have a y component, and it's also going to have an x component. And the combination of those two dictates the motion of the ball. But what if there were a third vector in here, which there could be? Anybody who's ever played baseball on a windy day knows that the wind can affect the baseball. Well, if I had wind blowing this way, this wind is a vector. It's going to be a velocity on this ball going this direction. Well, the x velocity is still bigger than my wind, so my ball is still going to move this way. Think about it. The wind never pushes a baseball entirely backwards, but it does push it so much that it doesn't go as far forward. And that's because this velocity adds together with this velocity. Well, this one is positive. If we assume that direction be the positive direction, this one is negative. So they kind of cancel each other out a little bit, which makes the resulting velocity this way less. And that's why balls that are hit into the wind don't travel as far. Now, on the flip side of that, if the wind were behind the ball, that's going to add to the ball's velocity in the x direction, and it's going to carry it further that way, because these two vectors would then add together and make the resulting velocity of the ball faster, which would make it go further. Here's another example to consider. A swimmer in a stream. Person swimming upstream. Let's say we're some Olympic swimmer and we know how fast we can swim. 2 meters per second, whatever the speed is. Well, there's a difference between swimming in calm water and swimming against the current. If this velocity is pointing this way and your velocity is pointing that way, they're going to work against each other. And your resulting speed, your resulting velocity is physically going to be lower. If I'm watching you on the shore, you still feel like you're swimming at 2 meters per second, but this velocity subtracts from yours because it's in the opposite direction. And from what I see, you don't appear to be swimming as fast because when these two add together, they cancel each other out. So if I wanted to graphically represent what my velocity is, if that's 2 meters per second, let's say this is 1 meters per second. 1 meter per second. My resultant velocity might be something like that. And notice I draw my arrow smaller than my original velocity because this has canceled out some of my velocity. Okay. We already addressed this, and we get how projectiles start off with a velocity, and that's some in x and some in y. And it's the combination of the two that result in the velocity of the cannonball. Up here, think about, we know at the highest point, the y velocity is 0. All the velocity is in x. So at that highest point, a cannonball is only moving that way because that's the only velocity it has. You can't add anything to it in the y direction because there isn't one. When the cannonball hits the ground, it has a lot more y velocity now because it's been falling from the highest point, has the same x velocity. So the resultant is going to be something like that. It's the addition or the combination of the x and the y. And if you've ever thrown anything and hits the sand or hits the ground, it goes into the ground at an angle like that because it has a velocity, which is a speed and direction, that has both x and y. Let's talk about some other vectors. Acceleration is a vector because it is a number. It's how fast velocity is changing. And acceleration is very definitely directional. Consider a rocket with its engines firing. The engines provide an acceleration. And if you've ever seen a rocket launch or you understand the concept, they speed up as they take off. And then they keep going faster and faster and faster because the engines are accelerating the rocket. Now, think about a rocket. As soon as the engines were to stop firing, then the only acceleration you would have would be gravity, and the rocket would start to come back down. So long as the engines are firing, we have an acceleration caused by this. We have an acceleration caused by this. So that the resulting acceleration, how much the rocket is changing its speed going up, depends on the combination of these two. Imagine this situation. If my rocket engine were only able to provide an acceleration of that, let's say that's the best my rocket engine can do. That's all the acceleration it can provide. What would happen to my rocket? It wouldn't get off the pad. It would not accelerate because we know that acceleration is 9.81 in the opposite direction. We'd be firing the engines and the rocket would just be sitting there. It wouldn't go anywhere because this acceleration and that acceleration would cancel each other out. So this acceleration, if it were 11 meters per second squared, well, now that acceleration vector is the bigger of the two. And when we add them together, we're going to get a little bit of acceleration in that direction. Okay. Now, let's talk about how this affects motion. Now that we understand that velocity can have an x component and a y component, and the motion of the object is the combination of those two, we can start predicting something about the motion of an object. Consider here a bowling ball going down an alley. And if you bowl like me, you don't bowl in straight lines. I roll my bowling ball down the alley and it never goes straight. So it has some velocity going this way. But if you bowl like me, my bowl always wants to try to go over here to the gutter. And the trick is with bowling, you need your velocity this way to be significantly larger than the velocity this way. That way, the ball hits the pins before it goes into the gutter. So for my bowling ball, at least, my resulting velocity might be something like that. Notice that my x component, my down the alley component, this one here, is a lot bigger than that one right there. And I would hope so. Because if this component of the velocity were the bigger of the two, your ball would go in the gutter every time. So if I know the speed of the bowling ball, if I know that speed of the bowling ball and I know the angle at which it's moving across the alley, I can figure out how fast it's going down the alley. And I can then change my motion to make sure that I hit the ball or hit the pins where I want the ball to hit them. Consider an airplane. An airplane flying along, its engines push it forward. And when airplanes get up in the sky, there's some very strong winds called the jet streams. They move hundreds of miles an hour. And if a plane is going across that jet stream, the wind is going to push the plane this way. A plane can actually have a velocity sideways, and they usually do. So the bigger velocity might be my engines from the plane, but I also have a velocity this way. So in the end, the plane moves something like that. That is my resulting velocity because I have a velocity going forward from the engine of the plane, then I have a velocity going sideways from the wind. Obviously, the bigger the wind velocity, the more my resultant is going to be pushed this way. If there's almost no wind, my plane is going to go straight because all velocity is just from the engines of the airplane. Okay. Now, a lot of practical applications to this. Think about you're a pilot and you take off and you're trying to go to Dallas over here, and you know where Dallas is, and you know how long it's going to take you to get there flying at a certain velocity. And so you think I'm going to travel in a straight line. I'm going to get to Dallas at 3 o'clock. But if there's a wind going sideways, your plane might wind up over here. And pilots have to account for the sideways velocity because the plane's not really moving that way. The plane's moving along its resultant velocity. So what pilots actually have to do is figure that out and point their plane in that direction so that the wind will push them and they'll wind up in Dallas. More common physics problem is something like this. So we have a boat, and a boat is trying to cross the river. And we usually know something about the boat. Boat's got an engine in it. And let's say the boat's engine can provide a velocity of 10 meters per second. And let's say here's the dock on the other side of the river. And let's say, let's say this river is 500 meters wide. It's something like the Mississippi. It's a pretty big river. Well, at 10 meters per second, what's it going to take me 50 seconds to get across this river and wind up right here. But as soon as I leave the dock, as soon as I leave this side, I've also got a velocity from the current, which is going to push my boat this way. Now I'm still moving this direction, but now I'm also moving this way. So my boat is going to do something like that because now I have velocity in two dimensions. I have some going this way and I have some going this way, but the physical motion of my boat is along that path there. And you can see why that's a problem because I don't want to wind up there. I want to wind up over here where the dock is. So if this velocity were 5 meters per second, let's say if the velocity is 5 meters per second, I wind up like this. What if the river starts flowing faster and the velocity ends up being 10 meters per second? Now my boat doesn't change. My boat still goes across the river in the same amount of time. But now it's going to wind up down there. If the river were calm, and let's say there's no current. It's a flat water river. In that case, I would wind up going straight across. In each case, my resulting velocity, my actual motion of the boat, is determined by the combination of the two velocities. One comes from my boat engine, and the other comes from the water. This is a lot like a projectile problem where you had a velocity in the x and you had a velocity in the y. Okay, so at this point, there is an assignment on Teams for you, or if you're in the classroom, you're going to be given an actual paper handout that has a set of practice problems with you about interpreting how vectors are added together, and then some calculation problems where we're given some numbers and we're going to figure out, okay, where does the boat wind up on the other side of the river? These problems will be gone over for you on the board tomorrow before you have your test on Wednesday.